Hello, in this video I want to show you how to analyze a simple 2D truss and optimize it and find appropriate cross sections and put criteria for displacement or other structural design goals. So first of all, I get started with drafting the truss that I want to analyze and optimize. So this is a 160 feet truss that I drafted in Rhino, and it is drafted in a way that each of the elements are defined as separate lines. Then I can transfer this geometry to Grasshopper by dropping the geometry components. Similar to other videos that I explained for you, you can drop the geometry parameter, give them names, and then when you are selecting the geometry parameter and right-clicking on it to set multiple geometries, you can pick for example, only bottom chords and set them to one single geometry, then top chords, then web members separately. Assigning these three different sets of members in a truss system allow you to apply, for example, the load condition into just a particular series of elements. So when you drop the geometry model, geometry parameter, and define the elements, then you're supposed to go to the model palette, create linear elements, and define lines as linear elements to be analyzed in Karamba. What I do here is that I'm going to define two different sets of elements. I connect bottom chords to one set of linear elements and top chords and web chords to another set of linear elements. And then I will give them a name. So for the bottom chords, I drop a panel and give it an identifier name, a text value. I call it A, and then for the other two, like top chords and web, I will just give them identifiers B and C. You may not remember how to do that to define a list. So if you drop a panel, right click on it and say I want to turn it into a multi-line data, then you can say, okay, I want to have B and C as two separate identifiers and connected to the identifier input. So in this way, actually, by using these identifiers, then I can just apply loads to, for example, only bottom chords, like the traffic load on a truss bridge. I connect the linear elements to assemble model component. Then I define two supports at the two ends of the truss. So what I do, I will just pick 2 points, 0, 0, 0, and 160, 0, 0 here, and drop the support component from the model palette and define both supports as hinge supports or pin supports. So I will just release RY rotation and then connect that to the support input at the assemble model component. Then for the loads, I just want to apply loads, a uniformly distributed loads on the bottom chords, like traffic loads. So instead of connecting all the elements, or using a list item to just say I want to apply the loads to just one single element, I use the beam identifier and drop a panel with a value. So here the load component understands that the loads should be applied to all of the bottom chords that are tagged with this a identifier. I call the load case 0 because I'm just going to have one load case. You can call it anything else. And then for the vector, I will just drop a z unit and give it a number. That number, for this example, is just set to -5 kilopounds per linear foot. And then you can make it global or local to the elements. Here in this case, it doesn't matter. And make sure that you're picking the block type of load that is a uniformly distributed load. Then here we're going to have the assembled model, and you can actually view what have you done so far before analyzing. So everything looks okay. I'm going to have just one load case here, and you see the loads are just applied to the bottom chords. Okay, now through the algorithms, I will drop the analyze component and get the results. So if I look at the analyzed model, and of course reduce the deformation scale, you will see that this bridge experiences a severe deformation. If you drop a panel to just measure what is the mass with a default profile and with a default steel profile, then you will come up with 20,000 pounds. And well, actually IBM, and then the maximum displacement is insane. It's 597 inches, which doesn't make sense. So that means that your bridge will fail. So we need to define an appropriate cross-section to make sure that our bridge has the acceptable load bearing capacity. So to get started with that, you can go to the cross-section palette and drop these 3 components. Material selection, cross-section range selector, and cross-section selector. So here, cross-section range selector, cross-section selector, and cross-sections. So what are these? The cross-section actually gives you a list of materials. You can pick whether you want to study steel, wood, or other materials. We go with steel, and then within the list of steels, within the diverse types of steel materials, you can go with all or pick a particular steel grade that you want to use to design your truss system. For this exercise, I will just go and say, well, let's go by all or like pick steel. And then the cross-section range selector, when you connect the material to the material input, will let you pick which steel product and which country you want to pick. So there is an inventory of the steel materials in Europe, UK, US, Russia, and other countries. We'll pick US. And then the shape that we want to use will be an I-shape beam. You can pick like pipes. Let's just go with I, and then within I sections there are again different types of sections. I go with wide flange beam, very simple. So we're going to pick wide flange beams for this optimization, for this truss analysis example. Then in the next step, we're going to select which type, which exact profile we want to select. So when you connect the cross-section to the cross-section input of the cross-section selector, then you should give it an index value of the cross-section. How can you figure this out? So if you connect the cross-section to a panel, then you will see the list of all wide flange beams available in Steel Manual. So each of these members on the bottom chord has a length of 10 feet. And definitely for web members, that length is greater. So if I just pick the index 0, I'm gonna actually select wide flange 4, which is a 4-inch depth with 13 pounds per linear foot weight of steel, which is a pretty lightweight steel profile. And then if I connect this cross section to the assemble model, you will see that the displacement is still horrible, 316 inches. That doesn't make sense. Although a wide flange profile has a, significant load bearing capacity, but still this is a very narrow and lightweight profile. So you can go with actually more deep and stronger profiles. So I go around wide flange profiles greater than, for example, 24 inches or maybe more. Without any calculation, you can get a sense of what should be the depth. So if you go by just like 1/10 of the length of this element, you expect to have like 3 feet, and then multiply it by 12 to just get by inches. So that would be a very deep beam. So I may go by 1/20th. And again, you'll see that it will be like a huge depth. So I should go with wide flange like 40 or something. But just let's pick something again lighter. So I'll go with wide flange 24 deep, and of course I'm gonna pick a light one, for example index 162. So I'm gonna just say 162, and then you'll see much better. So the displacement turned to be 37 inches. Now much better, right? And as the displacement gets better, then you will see the mass of the beam, the mass of the truss will increase, because we're going to use deeper elements and definitely a heavier element. Now it's hard to like do iterations and try different structural profiles, steel profiles, to get to the amount of displacement underneath, for example, a certain value. For example, if I want to limit the maximum displacement within the entire bridge to 9 inches, then I have to just try all of these elements one by one, which doesn't really make sense. So here is what we're going to do. We're going to optimize the truss. To do the optimization, cross-section optimization, you need to go to algorithms, drop the optimize cross-section component onto the canvas, and then you're going to connect the assemble model to this, and I'm going to just turn this off. Okay, so I'm going to connect the model output from assemble model to the optimized cross-section model input, and then I'm going to give the output of cross-section range selector, which tells the optimization component that pick appropriate cross-section from wide flange beams. So I'm going to connect this cross-section to the cross-section input of the optimization component. And here there are some other criteria that you're going to define. So we want to optimize the truss and make sure that the maximum displacement in the truss is less than a value. Usually we try to reduce the maximum displacement in a truss to 1/20th of the length of the span. And 1/20th of this span, 160 feet, will be 9.6 inches. So I will say limit the displacement to 9.6, and here under the setting there is one other input value which asks for the number of displacement iterations. So how does this optimization component work? This optimization component start trying different wide flange beams from the index value that you set here. So from here, it starts to one by one drop the wide flange beams that allows to reduce the maximum displacement underneath 9.6, and then captures the amount of displacement and then try another one, and again see what is the displacement by the next one, and then go to try another one. So this iteration will be limited to the number of repetitions that you define here. So I just said number of iterations for displacement is 20, so I'm asking the optimization component to do this iteration for 20 times, and just see what is the wide flange beam that allows to have a displacement less than 9.6 and at the same time has the less weight. So when the component does this procedure, we'll see that we'll end up with the maximum displacement of 8.4 with the mass which is pretty much greater than what we had here, almost 3 times heavier, but we could reduce the displacement. And then you may say, okay, now what are the outputs? How can I figure out that? What is selected? So you can get the outputs here. So it explains what kind of a system we have, and then we're going to actually see the design by viewing the model and viewing the beam. So through the model view, you can see the deformation, reactions here. I'm going to reduce the scale of the fractions. Still pretty large. Okay. And then the beam view here let you explore, for example, what is the maximum bending in truss elements, or what is the axial forces experienced in the structural elements. I reduce the scale, but still you see that elements are experiencing heavy axial loads, which is okay. And what you can actually see is the axial stress in the beams. And also you can see the cross sections. And you can see the stress to strain ratios. These diagrams can be displayed like axial stress or displacement, or stress to strength ratio can be displayed through diagrams. As you see here, the elements are colored, and in order to see what are the values based on the color, you can drop a color component. Oh no, sorry. Go to the where's that? Utility. Legend. And when you drop the legend, you can connect the color, and then you can connect the legend tags, and then like stretch it like this. And then based on the legend, you can understand, for example, like the dark purple represent how much of displacement in inches, or for example the axial stress here. Negative represent compression stress, blue represents tension stress with positive values. So as you see here, the elements in the bottom are under tension, the elements on top are under compression, and based on their colors you can actually see what is the stress value in KSI. So this is one way to see the axial stress. And what else you can get from these diagrams. And then under the model view, under the annotations, you can say you want to see the element numbers and element tags, cross-section names. So by turning on the cross-section names, you can actually see what are the cross-sections assigned to each of these elements. So wide flange 12 by 210 is assigned to the bottom chords. Then wide flange 14 is selected for the top chord, and then the other one, the webs are done by wide flange 8 by 687, and of course that is different from like web to web or element by element, so it's not like all the same, but you can actually see how the optimization component pick the appropriate cross-section to meet the displacement limitation and at the same time minimizing the total weight of the truss system. So this is how we can start to study different profiles for getting the most optimized truss design.